Okay, so if there are no questions, then we can start today. So the topic we're going to cover today is semantic segmentation. And in the last, I think, couple of lectures, we talked about image segmentation, and they are very much related to each other. So for image segmentation, what you do is you divide different segments of your image, and we learned like different approaches to do that. We started like very basic, where we learned how we can do image binarization, right? So just dividing the image into foreground and background. And then we also learned some more sophisticated algorithms where we actually divided different regions, try to group pixels into those. And again, we discussed like a lot of different approaches. We started from region growing, region splitting. Then we talked about clustering. So even in clustering, I think we talked about two different algorithms. So there the goal was to split your input image into different small regions. And those regions may indicate some like semantic object in your image, or they could be like just a part of that semantic object, right? So that was image segmentation. And whatever result you get, you don't know any semantic meaning to those regions. So this image segmentation algorithm will just give you those regions. It will never tell like what that region represents. All right. So that's the biggest difference between image segmentation and semantic segmentation. So in semantic segmentation as well, what we are going to do is we are going to divide your image into different regions. But the difference will be each region will have some semantic meaning. So you will know what it represents. So for example, in this particular case, you can see that you are dividing this into, again, two different regions. So you can also compare this with image binarization, because there as well you were doing background, separating the foreground from the background, right? So two different regions, and it's doing exactly the same thing. But the difference here is that you know the background is grass and the foreground is a sheep. Okay. Now, another detail you need to know is, so you're not just assigning a semantic label to a bigger region, right? So if you do that, that's more close to object detection, because that's what you do in object detection, right? So you, for each object, you detect like some kind of bounding box, and then you know that that bounding box represents like one particular category you have in your data set. So then there you have just one annotation for the whole region, right? But in semantic segmentation, the difference is you have that semantic meaning for each pixel. So even though this is like one big region, the blue one, which is representing sheep, you know that each pixel in this region represents a sheep. So it's not just one label per region, it's one label per pixel. Okay. And so one big challenge in semantic segmentation is how we can obtain annotations. Because as you may have already like judged this, if you need like annotation for each pixel, then obtaining ground truth or obtaining annotations for such a training will be very difficult, right? So you need annotation for each pixel in comparison to like annotation for each bounding box. So the complexity is increasing. Now, so we do have some existing data sets to solve this problem of semantic segmentation, and these two are like one of them, Pascal VOC and MS Coco. And in these two, like we have pixel-wise annotations. We have many other like data sets for videos as well. So in videos, I think we have A2D, that actor to action detection. Again, you can call that as a semantic segmentation in terms of activities. We have, I think YouTube was, and we have one more, I think VOS dataset, and that's also for video. Now, another interesting thing here you can note is, So for all these data sets, what you have is you have for each pixel, you know which semantic category it belongs to, right? So let's say you don't have annotation for each pixel. Then what usually we can also do is if you have a bounding box here, which says that this bounding box belongs to sheep, then what you can do is you can actually propagate that label to all the pixels which are inside that bounding box. And in a way, you are converting your easy annotations, like which is just one annotation for bounding box, to like all the pixels inside that bounding box. So it's kind of dense prediction. And of course, like such annotation will not perform as good as this kind of annotation, but that's like another variation. If you don't have enough annotation budget, you can do that as well. So semantic segmentation, it's like a key part of scene understanding. And there are a lot of applications where this can be used. So it can be used in autonomous vehicle. They can be used for assisting like people who are partially sighted. Then I think there is a big application in medical imaging. And of course, like for image processing and image editing, you can use it. So for autonomous navigation or self-driving cars, you will have different kind of sensors, different kind of cameras in your car, which will allow like that car to make a judgment of what are the different objects present in the surrounding or in the road, right? And to make sense of that, what you'll have to do is you'll have to perform some kind of semantic segmentation like this. So if you can do that, then the algorithm, whatever algorithm which is like running that car, it knows that which object categories are present and where exactly they are present, right? I mean, of course, I mean, you can also use some kind of object detection, but if you have a semantic segmentation, it is more precise. And in case of self-driving, I think that's very useful. The other application could be, as I said, like it can be useful in assisting partially sighted people if they can't see well. So if we use some kind of camera to record like their line of sight, and we perform this kind of semantic segmentation, then we can give a feedback to the person that what different objects are present like in the scene. And in medical imaging, there are a lot of applications. So all kind of like CT scans, the radiographic images. Sometimes it's very hard for the doctors to like analyze all those images manually. So the idea is like, can we use computer vision to automate some of those tasks, and segmentation or the semantic segmentation is one of them. So in this case, I think it's trying to find out like if there's any issue with the lung over here. And I think the red region is trying to segment that part. And of course, like for your Photoshop, and if you want to do some kind of image editing, this can have a lot of different applications as well. Okay, so in this case, we are showing here like a sample image from one of the data set. This is Pascal UC 2011. And here you can see that we have the ground truth annotation, which is available, which you can use to train our models. And one big difference between semantic segmentation and then instance level semantic segmentation is that in instance level, you have to tell like which category each pixel belongs to, but then you also have to group those pixels which belong to like one particular instance. All right. So let me try to explain that. So let's say you have this input image, and if you focus on the chairs here, so you have 4 different chairs, right? So if you're performing just semantic segmentation, then each of these pixels should say that it is a chair, right? And they don't care about like there are 4 different chairs. So that's semantic segmentation, the annotation you have on the right. So you're not differentiating between different instances of chairs, right? And the second category is instance segmentation, where you have to tell like each pixel belongs to what category. But if there are two instances of the same category, you will have to set them apart as well. So in this case, you will tell that, okay, there are chairs, but then you can also try to predict that this pixel is a chair, but it belongs to one particular instance. And this is like another instance of the same category. So this is instance segmentation. It's more difficult than just doing semantic segmentation. And we will see like how we can solve both these problems. So one may ask like, so what happened to like these objects in the back? Of course, we care about those as well, but these are pretty small, and I think these categories are not present in this particular data set, but if someone wants to include those as well, they can annotate these objects, and probably we can increase the number of categories. I think in Pascal VOC, we have just 20 object categories. And in the other one, MS Coco, we have around 80 subject categories. So that list is not comprehensive, so it doesn't cover like all the objects. Now, before 2013, I think, or 2014, when like the first deep learning papers for image segmentation came out, so most of the research was just like without using neural networks, and there are a lot of good techniques to perform this task. And these are like some of the approaches: text and boost, text and forest, and this conditional random forest. So this is more recent, and what people have done is they have tried to combine this CRF approach with a deep learning approach, and it has been shown that if you do that, it kinds of improve the results whatever you get from your deep learning model. But I mean, there are other instances as well where you don't need these conditional random forest and still get good results. But yes, I mean, of course, people have tried this and combined this with deep learning. So there are good methods for that, and they perform pretty well. So we are not going to discuss like these classical approaches. What we will discuss is we'll talk about what are the latest deep learning models which can be used for solving these two tasks: image segmentation and semantic segmentation and instance segmentation. So before we begin, just a quick recap, and I think we have covered this in one of the lecture where we are talking about, I think, convolutional neural networks. So a standard CNN where you are performing a classification task, right? You have an input image, and then you will have several of these convolution layers. And some of these layers will be followed by max pooling layers to reduce the resolution of your feature map, right? So it's you have one max pooling layer over here, then another max pooling layer over here, and then these are like consistent. And at the end, when you're done with like your feature extraction using CNNs, what you usually do is you flatten your features, right? You might remember that from your programming assignment one. And then you add a couple of like fully connected layers. And at the end, you have a like final fully connected layers, which make the prediction about all the object categories you have in your data set or which you want to classify. So this is a standard CNN classification network. And in this case, you have these fully connected layers. Now, another view of the same network can be a fully convolutional view, and which allows you to use the same network for different resolution of images without any issue. And in fully connected layers, if you have trained that network on certain resolution, then you cannot change the resolution during testing, right? You will have to use the same resolution. But once you have this fully connected layer, and we already know like how to do this conversion, these should be like just 1x1 convolution, and then we know that both are like they can be interpreted as the same method. Right? There is no difference in like what computation we are doing. But the benefit here is that if you are training your network, which is fully convolutional, on certain resolution, then if you use like a different resolution as input, even then your network will be able to produce some results. And the reason for that is the kernels you have in these layers. So they are shared across all the locations. right? So you don't have different kernels for different locations. So then that's why if you increase the resolution of your images, then it's not going to like you don't need to change your network. The only just hold on, give me a minute. Right, sorry about that. So what I was saying is, if you have a fully convolutional network, then you can change the resolution of your input and still you won't have any issue. The network will predict something. The only difference will be the shape of these feature maps. So the shape is going to change because if you increase the resolution of your input image, the resolution of this feature map will also increase proportionally, right? And subsequently, like for these feature maps as well. And at the end, what's going to happen is your output will be, let's say if it had like certain resolution, so the resolution of the output will also change. So that will be the only effect. Now, the same idea of using a fully convolutional neural network can be used for image segmentation or semantic segmentation, and we'll see like how we can do that. So this was, I think, the first paper, one of the first paper, which does semantic segmentation using fully convolutional neural networks. And the idea here was you have an input image, then you get rid of like all the fully connected layers and convert them to just convolution layers. And at the end, what you will do is you will try to predict 21 different channels. And these 21 different channels are for 21 different object categories. In fact, we have 20 different object categories. So this network, I think, is for the Pascal VOC dataset. So there are 20 different objects there. So each channel is for each object category, and one is for the background. So background in this case, like if it's black, so that's like one additional negative class you have. So in total, you will have 21. And that's why the number of channels you will have 21. And what you will do is each pixel location in each of those channels will tell you whether this particular object category is present in that pixel or not. And later on, they try to like upsample that to the actual image size, and then they can train it like end to end. Okay. So one good thing about this is what you can do is if you have pre-trained your classification network on, let's say, a very huge data set, which could be ImageNet or something else, then it means that you have already learned good filters for feature extraction in these layers. And once you do that, you can actually use those pre-trained weights to perform this semantic segmentation. Right? The only change you will have to make is you'll have to get rid of like the final fully connected layers and replace them with convolution layers. So those will be the only layers which you will have to learn on the task of your semantic segmentation. Okay, so one interesting idea here was the use of skip layer. And the idea was in these earlier layers, the features you have, these are like features at a higher resolution when you compare those with these later layers. And then these layers will have some kind of finer details about the structure of the input image. So the idea is like, what if you use features from these earlier layers, which are of high resolution, to make these predictions? And that idea actually works pretty well. And later we will see, like in almost all of the networks which we're going to talk about, we do have those kind of skip connections to improve the performance. Okay, so that was the idea. You convert your fully connected layers to convolution, and then you can use your existing network for that. And this is the idea about those skip connections, or they call this skip layers. Now, this is your original network, the same network here, right? So, and this is just showing like the pooling operation, how the spatial resolution is changing over time. And the final output is like this one here. So it's pretty low resolution. So what they do is they just upsample it to the resolution of the original image, right? And this 32 times means after performing these convolution operations, the original, the height and the width, the resolution was reduced to like 32 times. And that's why they have to increase this like to perform an upsample and increase the resolution 32x times. Okay, so that could be like your one result, which is coming out of your final layer, and it will be at a very coarse level because you don't have very high resolution features here. Then what you can do is you can try to perform upsampling on the same feature set, right? And maybe you can go from 1x1 to 2x2, or it could be if it's 8x8, you can go to 16x16, all right? And then what you do is you take features from the previous layer which already had a higher resolution. So for example, if these features are coming from this particular layer, then this pool 4 is coming from this particular, which is like twice as big as this, right? So what you do is you take these features and combine these two. So these are the original features, these are the upsampled version, and then again try to upsample. So this time, because you increased by twice, so it is just 16 times upsampling. And you can do similar operation for previous layers. So that's how you try to use these skip layers and improve the quality of your semantic segmentation. And so here are like some sample results, how they look like from these different upsampling operations. And so this is the ground truth. Right, so you can see here that you have 1 to 3 different cycles and you have 3 different person. And it's not instance segmentation, it's still just semantic segmentation, because you can see that you have 3 different people here, but you don't care about that. You're just saying that each pixel belongs to person or not. Each pixel belongs to cycle or not. So you don't have any way to tell that these two are like different instances, okay? So we are still talking about just semantic segmentation. Now let's look at like the prediction which you're going to get from this final layer, and this FCN32S is showing the results after that. And you can see here that the quality, I mean, it's not that good. It's just giving you a notion that kind of mean you have a person present here, right? Or a person present here, but it's the shape information is totally gone. If you look at the cycle, it's like, by looking at this blob, you will not be able to predict this is a cycle, but because the prediction is saying that this pixel is cycle, you can tell that. Now that's the prediction from the final layer, the lowest resolution. So if you move one step up to 16 times, so you can see that the boundaries are much better than the first image, right? And this is like the previous layer. You can see that they are improving, and you can do that for multiple layers, and I think the quality will still improve. But one issue here is that you can observe that this is like taking some toll in terms of memory, right? So this will take additional memory when you compare with this. And as you move ahead, like into the network, so you will have high resolution of features. So then reusing those features again will take that amount of memory again. So you're also increasing the memory consumption. So that's like a trade-off between how much memory you need and what kind of performance you will get. And now here we talked about like we can upsample your features, right? So this was upsampling to 32 times, and this was upsampling to 2 times. So you were, if it was like 8x8, you're going to 16x16, and similarly you are increasing the resolution here. Now the question is how exactly you have to do that. So again, there are different methods to perform this upsampling, and we will look into some of those. The easiest way is nearest neighbor. So what you do here is if you have like an input feature map of size 2 cross 2 and you want to move to 4 cross 4, then you will increase the resolution and then you're just going to repeat the values from each pixel to the nearest pixel locations. All right. So that's just repetition, and this is called like nearest neighbor upsampling. I think there is a question from Furkan. I did not understand the reason why we use many conv layers if we are going to upsample them to mask our objects. Okay. Now, when you have these layer of convolution operations, so the idea is you also want to predict like which object category you have, right? You just not only want to do this segmentation. Now, to be able to predict that which particular category you have in this particular pixel location, you might need to look at a bigger context. And then what's happening is if you have like a pixel activation map or activation value at this particular location, the receptive field of this will be like, I think the whole image, even bigger than that. It means that the value you have derived at this location, that inference is based on some kind of manipulation or transformation on the data which you're looking in this image. And that's why you're able to interpret, okay, so this pixel belongs to cat or this pixel belongs to dog. On the other hand, if you're saying that you just only want to use the initial layers, then what's happening here is that each pixel location has like a very small receptive field. So if you, let's say, if you look at this particular location on this left top, right? So the features or the activation at this location was computed based on some kind of convolution operations in this particular region, right? So even like as a human, if I will give you this particular patch, let's say the smaller patch, just all pixels black, then I don't think you will be able to predict that it's a dog because all you're seeing is just a black patch. So therefore, like to understand what object category is there, you need to look into bigger context. So you need to extract features and do some learning. Okay, so I hope that was clear. I think it's not. So you're saying if don't want do object detection, but just segmentation, then we don't need to downsample the images, right? But still, like if you want to perform segmentation, as I said earlier, like if you want a method which can segment like a fine boundary like this, you need to look at the whole context, right? Otherwise, how will you group like different regions together? So to make that connection that this patch belongs to the same object category as this and then connect them, you need to have multiple layers. All right, great. So this is like the simplest method to perform upsampling. You just repeat the values. The other interesting method, I think, which is most of the times I think we use this, it's called bilinear interpolation. And it's pretty simple. Again, if you have, let's say, 2 cross 2 patch and you want to perform a 2x upsampling, so that will give you 4 cross 4. Then what you do is, so these 4 pixel locations will go in the corners, right? 10, 20, 30, 40. And the upsampling is performed in these intermediate pixel locations. And to find these values, what we do is we simply perform bilinear interpolation of these corner values. Okay. So in fact, what we're doing is we are just creating space in between these two. And then next step is like to fill up those values. Now, to fill these values, what we do is, so this is a simple formula. And I can briefly try to explain like what this is trying to do. So bilinear interpolation is, let's say I want to find a value for this particular location, and I already know this value and this value, right? So what I will do is I will take a weighted sum or a weighted average of these two values, And based on like how far away this pixel location is from these two locations, I will use those as a weight. So let's try to figure out how we can do that. So for this particular location, you can see that this is 1, 2, 3 steps away. Okay, and this one is 1 step away. So the weight for this will be 3/4. Okay, and the weight for this will be 1/4. And then you just use those weight and take the linear combination. So I think it will come around to 15. So that's what we are doing here. So just ignore this first term and also ignore like the second term. Just look at this. So in this one, what we're doing is we are saying that, so this is just in the X direction, right? So let's say this is the X direction and X1 is this first location, X2 is the second location. So what we do is, and X is like the target location for which you want to find the value. Let's say this is the second location. So what we will do is we will find this distance, X2 minus X1, how far this is, and divide it by like the total distance, which will be X2 minus X1, and then we multiply that with this Q1. And similarly, we'll take like X1, this minus this over the total distance and multiply with this. So that's like the linear combination. And if the location for which we need to compute the value is between these two locations, then we only need this operation. But we will need the full equation when we have a location, something like this in between. So for this one, the 4 nearest known values are these 4. So then what we'll have to do is first we'll have to perform linear interpolation along this direction. So we'll get this value, which is done by this operation. And then we will perform linear operation between these two in the X direction, get this value, and it is doing the operation. And then we're going to do the interpolation in y direction between this value and this value. So this 32 value will be outcome of this operation, 12 will be outcome of this operation, and then again this is the same formula which you used inside, right? So then you linearly interpolate between these two, you will get the value you want. Okay. So what is the value of X? So this X is the location. So for example, in this particular case, this is 0, 1, 2, and 3. Okay, so it's used like to get the distance between these two locations. So Jiangtai, could you please plug in the numbers to one calculation? Okay, all right, let's do that. Let's try to compute these two. Let's do the computation for this particular value. So for this, we'll have to first find this value and this value, and then we'll figure out this. All right. So for this one, this is the equation, right? So the distance from this to this is 1, 2, 3. It's 3 steps, right? And total we have 4 steps. So this becomes 3/4, and Q11 is 30. So 3/4 and then 30 times. You can maybe take a pen, and I'm just doing it on my mind. So 3/4 and then 30, and the other one will be, this is distance 1, okay? So X minus X1, and again this is 4. So 1/4 and then by 40. So this becomes 40/4, 40/4 and then 30/4. So 30 and 3, 90/4. 9 and 4, so 130/4, right? And 130/4, I think that will be somewhere around 32. So if you do the round off, okay. So similarly, I mean, I think you can do that for this 12 as well, and then the same equation for 32 and 12. Okay, great. So now the other operation which we can use for upsampling is we can define like max unpooling. Okay, so this is like a kind of your autoencoder, which you did for, I think, your programming assignment too. And the encoder will try to learn some kind of latent representation, so a reduced feature map, and then you will try to upsample that. Okay, so what you do is in your encoder, there will be times like when you have to perform max pooling. Okay, so when you perform max pooling, for example, in this particular case, your input is 4 cross 4, and you perform a max pooling by a factor of 2. So what you do is you take the maximum value, right? 5 over here, 6 over here, 7 over here, and 8 over here. Now, in max unpooling, what you do is you store this map like from which particular location your values were picked. So this heat map where it says that this value, this value, this value, and this value were picked. So you keep a note of that. And when you're performing upsampling or unpooling, what you do is you make use of that. So for example, you were at this particular location and you perform a max pooling like this. So you will store this map, and when you are upsampling like at the same resolution in your decoder, what you will do is, let's say this feature map has value something like this and it's 2 cross 2. Now what you will do is you will use the same max pooling map to perform this unpooling. Now let's see how we can do that. So you have to replicate 1 4 times, but the location where you will propagate this value will be based on from where exactly you picked the max pool number while you are doing max pooling. So this 5 was picked from this location, and therefore this 1, when you upsample, it will go into that location. So you can see the same location, and rest you will just put 0. Similarly, like this number 2, you will put at that location from where it was max pooled. Okay, same for these. So that's called max unpooling. And the idea here is so what you're doing here is you're trying to get like values which are high activation, right? And you're kind of remembering from which location actually you got those activations. And therefore, these activations you are just transferring back to the same locations. So it's kind of refining your features from there where they came, just putting it back there while you're doing your upsampling. Okay, so question from Sunil. Are we keeping track of those locations somewhere where dump? Yeah, we are. So we are storing these values. So we are just keeping a track from where you max pooled. So for each max pooling operation, you will have such kind of heat map, which you're going to use in your decoder part. Okay. So this is called max unpooling, and we'll talk about like one network where we use this. Now, those are like simple upsampling where you don't perform any kind of transformations. It's just propagating values or repeating values or doing some kind of interpolation. So there's no learning involved. Now, there's another way to perform upsampling and also do some kind of learning. And there are different names to this. This is called deconvolution. You can also call this transpose convolution. And I think there are some other names as well. And so, and again, there are different ways how you can do this. I'm just talking about these three, but there can be other ways as well. And which one performs better? It depends on what you're trying to achieve. So there is no like ground rule. You should use this kind of deconvolution and it should work. And most of the times what will happen is if you just perform normal convolution in combination with upsampling, that usually works, I think, almost similar as your deconvolutions. So those are like just practical aspects, but let's see like what deconvolution is trying to do. So this is your input feature map. Okay, so it's 4 cross 4. And let's say you want to increase the resolution to 6 cross 6 or 7 cross 7. All right. Now, what it's trying to do is for each pixel location in this input map, it's trying to learn a kernel, and it's different than convolution, where what we try to do is we try to learn a kernel for like multiple pixels. For example, if you have a 3x3 kernel, so what you do is you apply that 3x3 kernel into a local neighborhood where you would have those 3x3 or 9 pixels, right? And you will apply that kernel and get just one value. So that was like moving from 9 values to 1 values. But in deconvolution, you still have that kernel, but instead of like using 9 values and coming to 1, you are going to use one value and go to 9 different values. Okay, so it's like it's a different direction. And the way we do is you put your kernel at this location, let's say, and you multiply this value with your kernel values. So then what will happen is it's kind of element-wise multiplication. So uh, you're just amplifying the activations you have in your kernel based on your input feature map. And if let's say you're using in this case, you're using a 3x3 kernel, so you will take one location and it will give you 3x3, 9 different values, which you will put at this location. Okay. Now, be careful here, because what's if you check what's happening, so these 3 locations, you will get values from this. But as you move to this location, you're again getting these 9 values. So you keep accumulating those values. So it's not that each location is only getting value from one pixel. So depending upon where that pixel location is, it might get values from multiple locations. So you will keep accumulating like those values as you move or stride your kernel in this input feature map. Okay, so this is the deconvolution, one type of operation. Now the other is, and again, this is like, this is a nice way to say it's a deconvolution, because in fact, you're moving from 1 pixel to 9 pixels. And this is in contrast to like what you do in convolution. But the other variations which are going to look, they are still making use of convolution operation. And let's see like how they're trying to increase the resolution. So in this case, you have a 2x2 input feature map. And let's say you want to move from 2x2 to 4x4. So what you will do is you will just perform padding of this input feature map. In this case, there's a padding of 2 from all the 4 sides. And you take a 3x3 kernel and just take your normal convolution and slide it over. And this is going to give you a 4x4 feature map. Okay. This is another variation. And so in this case, you can see that most of the convolution operations, like which are along the border, most of these will be 0, because you're just using the padding. So to resolve that, what you can do is you can actually increase the stride in your input feature map. Okay, so this is some kind of padding in between. And again, so in this case, you have 3x3 input feature map. So the input feature map is only like the blue values, and the white one is the padding. And again, you can perform the same convolution operation which you do in your encoder. And I think this is moving from 3x3 to 5x5. Okay. And there are like some pros and cons of this. So in this case, I think if you use this for, let's say, some kind of reconstruction task or super resolution task, then in the output, I think what we see is we see some kind of checkerboard effects, and that happens because of these atrocity in between, or the stride in between. So those were like all the upsampling operations. And of course, there are many others as well. This is not an exhaustive list. Okay. Now let's look at like one of the semantic segmentation network. This is called semantic segmentation using deconvolution. And the idea here is you have the input image, you have the convolution network as encoder, and then you have a decoder which is making use of deconvolution operation. And here you can see that for the upsampling, they are making use of unpooling. So this is the same unpooling operation which we just discussed, where you actually keep track of how you perform max pooling in your encoder. and replicate like that transition of pixel values in this upsampling layers. And so this is traditional CNN. So these are con layers, max pooling con layers. That's fine. And at the end, you have a flattened feature vector where you have 1x1 convolution layer. And again, these are unpooling layers, and these are deconvolution layers. And they are, I think, making use of this deconvolution operation. Now, one thing you might notice that you are increasing the resolution from 7x7 to 14 using unpooling, but when you're doing deconvolution, your resolution is not changing. But in all the variants we saw here, you can see that the resolution is kind of increasing, right? So what they do is they perform this deconvolution and then they chop off the borders. So if it's 4x4, they will only take like 4x4 values from the center. They will just ignore the border values. And that way they keep like the resolution consistent. So 14x14, 20x56. So this is not normal convolution. It was deconvolution. Okay. So that's one kind of network where one drawback is like you need to keep track of how you perform max pooling to perform this deconvolution. Okay. So question from Sunil, how they are keeping resolution constant? So let's say you are performing this deconvolution operation, right? So your input is 4x4, and let's say you're using a 3x3 kernel. So you will repeat these values. So your feature map will be, in this case, it's 6x6. So what you're going to do is you're going to ignore the border values. So you will just crop your output feature map and take a 4x4 activations from this region. Okay. Is that clear, Sunil? Okay, great. Now, so these are some sample results taken directly from their paper. This was the input image, and these are the results after like the deconvolution layer, which is at this level, 14x14. And this is like what happens after you perform unpooling layer. So you remember that unpooling is you transfer your values to different pixel locations based on your max pooling operation, right? So that's why these pixel values are scattered after this unpooling operation. And then again, the deconvolution operation. And here you can see that again, these values are scattered. So as you move on, so this is like the original shape 224, 224 deconvolution. We can see that this is a very nice segmentation of this bicycle. Hello, everyone. So let's start. Is my audio fine?
Yes, Professor.
Okay, great. Thank you. All right. So last lecture, we were looking into fully convolutional networks for semantic segmentation. And then we discussed how we can use like any standard CNN architecture which we have defined for classification, and maybe modify like some of the later layers where we have fully connected layers, just convert them to fully convolutional using 1x1 kernel. And then we can predict these activation maps which represent the segmentation which is required. And we can also improve the quality of this segmentation by performing this upsampling and also taking features from intermediate layers. So the prediction from the final layers, which is actually very low resolution, will give you very coarse segmentation. And if you start picking features from some of the earlier layers, then you will get like more finer details, the boundary details for the segmentation. And then including these features will lead to like these improved boundaries. So here you can see that this is like very coarse level prediction and how the boundary, for example, for this bicycle, it's It's not even close to bicycle, right? It's just a blob, and how it's improving as you include like features from these earlier layers, which is like high resolution when you compare this with the final ones. Okay, so that was the trick. Then we talked about how we can perform this upsampling from a low resolution to high resolution, and there were some simple techniques like nearest neighbor. Then we also discussed bilinear interpolation. So there was a question how exactly this is done. So I think Jengta, you were confused. So now is this clear to you? Okay, great. So then we can use this interpolation for upsampling. And then there was a very nice trick for performing max unpooling, which is actually a very cool idea. What we do is, because in semantic segmentation, you'll have this kind of symmetric structure, right? The encoder part, which you use to extract the features, and then the decoder part, where you are going like from the latent feature space to again reconstructing the segmentation map at a higher resolution. So the trick was, the way you are doing max pooling, just repeat that to perform the upsampling. Because max pooling is like selecting from which particular region, like if it's a bigger neighborhood, so which pixel you take the activation from. So this is kind of giving you the fine level localization detail from exactly where in the image you picked that feature. So then in upsampling as well, when you're decoding, you will put back the features to that particular location. So that will help you in like localizing your boundaries or your objects when you perform decoding. So that was a nice idea where, and we can use that for max unpooling. You just propagate the values. And then there were some like learning techniques, like instead of just doing upsampling, you learn how to do upsample. And that's again using these convolution kernels. So we saw different variations of that. Okay, so this was like one network where unpooling and this deconvolution layer was used. And we discussed these results. Then this was another network which is called SegNet, and this is very popular, not just in semantic segmentation, but if you have to perform any task where you need like going from one domain to the other. So it could be your image to image translation, right? For example, you have an input image and you want to draw a sketch of that. So wherever you need that kind of auto encoding, this SegNet kind of a structure is very powerful. Now the difference between this network and the deconvolution network, which we discussed on this slide, is mere like this convolution operation. So in this case, we are performing deconvolution, and we also discussed like how we are also maintaining the spatial resolution in this deconvolution operations by trimming the padding, the boundaries, just keeping the center region, right? So in SegNet, instead of using deconvolution, we just use the normal convolution, and we still have this unpooling layer. So for upsampling, we are using unpooling. So this is showing like the pooling indices transferring from your max pooling to unpooling. And there are some other changes like after con, there's this batch normalization, which has other benefits, but the main difference is this conv operation. Okay. Then this was another interesting architecture. And so most of the time what we do is we take like a combination of this UNet and this SegNet. So we don't perform this pooling of indices. We just take the features as it is, and we instead of unpooling, we do this upsampling, right? Using interpolation or maybe just repeating the values. And instead of cropping the input feature space like this, we can actually just take the full feature map here and concat, and that is possible if your resolution of feature maps at this level is same as this. So which is the case for SegNet, right? The resolution is same at the corresponding layers. But in UNet, since they are not maintaining the resolution as they perform convolution, and that's the reason when they perform upsampling, the shape of these activation maps is different from the shape which was in the encoder. So for example, if you look at these subsequent convolution layers, the starting resolution was 284. And since they are not using any padding, so after performing convolution, the resolution is just 282. And again, it reduces to 280. So, and it's not matching with what you have here. But instead of this, if you were to maintain the resolution and let's say you perform a padding of 1, and in that case, what you can do is you can maintain the resolution. So it will be 284 all the way in all these 3 layers. And after downsampling, when we will come back after upsampling, again, you will get your same resolution back as 284. And then what you have to do is you don't have to perform this cropping. You can just directly use those features and perform this concatenation here. Okay, so that's the standard like variation, which is very highly used. Okay, so the difference between UNet and SegNet was, one difference was instead of unpooling, we are just using upsampling. The other difference was we are propagating like or using features from the encoding part in the decoder.